kiddos, welcome back. And on this video, we're going to continue our discussion of colligative properties. The last video, we talked about vapor pressure lowering. Today, we're going to talk about boiling point elevation and freezing point depression. Hopefully, these will both make a bit of sense. If you remember, in the last video, a non-volatile solute will lower the solvent's vapor pressure. I think we established that. If we add something like sugar or salt to water, its vapor pressure will lower. It turns out it also affects the boiling point of the solvent. Now, if you remember your definition for boiling point, I know this was several weeks ago, several videos ago. A liquid will boil on a stovetop when its vapor pressure equals the atmospheric pressure. So we need to heat up that liquid enough so the vapor pressure of the liquid will equal the atmospheric pressure. When that happens, the liquid begins to boil. When the temperature of a solution containing a non-volute solute is raised to the normal boiling point of the pure solvent, the resulting vapor pressure is still lower than the atmospheric pressure. Remember, it's called vapor pressure lowering. So I've effectively lowered the vapor pressure of my liquid. So now, don't I have to add more heat to my solution so that there's enough kinetic energy so the liquid has enough vapor pressure to equal the atmospheric pressure. So it's still lower than the atmospheric pressure and the solution won't boil. The solution must be heated to a higher temperature. This is why it's called boiling point elevation, by the way, to supply additional kinetic energy needed to raise the vapor pressure to the atmospheric pressure. The temperature difference between a solution's boiling point and the pure solvent is called boiling point elevation. Now, there's an equation that goes along with this. It's right here. It's delta T sub B equals K sub B times M. Now, delta T sub B is the boiling point elevation. Okay, it's the change in the boiling point, and it will be higher than the normal boiling point of the pure solvent. K sub B depends upon the liquid, the solvent that you're working with, and that's called the molal boiling elevation constant. And the small letter m represents the molality of the solution. So right here, the temperature difference is equal to the molal boiling point elevation constant multiplied by the solution's molality. Now you're going to find that we often use water in these examples. Now water has a normal boiling point of 100. Its molal boiling point constant is 0.512 degrees Celsius per molal solution. And you'll notice that other solvents have different boiling points and different boiling point constants. So we just apply these constants to this equation and we can find the boiling point elevation. Now, along with boiling point elevation, a solvent's freezing point temperature will also change. The particles no longer have sufficient kinetic energy to overcome the intermolecular attractive forces. The particles form into a more organized structure in the solid state. In a solution, the solute particles are now interfering with the attractive forces of the solvent particles. They're literally getting in the way. This prevents the solvent from entering the solid state at its normal freezing point. So we need to lower the freezing point even more for that to happen. Now, the equation for freezing point depression you're going to see is very similar to the equation for boiling point elevation. We have delta T sub F, which of course is the change in the freezing point temperature, and that will equal K sub F, which is the molal freezing point depression constant, and small letter m, which is the molality. Once again, we like water lots. Its normal freezing point is 0, and its freezing point constant is actually it's a negative 1.86 degrees Celsius per molal solution. So for every molal solution I have, the freezing point of water will drop 1.86 degrees. If it's 2 molal, it will drop 2 times that amount. So you'll notice that other solvents have different freezing points and different freezing point constants. Now, what effect does this have on the phases of my substance? You'll notice this here is the phase diagram for water. I happen to know this is the phase diagram for water because I noticed this slope of this line right here is negative. And it's pretty unusual that, as you're aware, that a substance has a negative solid liquid slope, unless, of course, it's water. So, at 1 atmosphere, let's see, here's normal freezing. Oh, look, it says water right here. Normal freezing point of water is, let's see, 1 atmosphere. Looks like it's going to be right about there, right? Now, what happens when I add solute to my solvent? Well, we just established that the freezing point is lower than it would normally be. So, it looks like at 1 atmosphere for my solution, the freezing point is now at a lower temperature. It stays in the liquid phase at lower temperatures, doesn't it? Hey, let's take a look at the boiling point. Now remember, normal boiling point and normal freezing is when those phase changes occur at 1 atmosphere of pressure. Here's the normal boiling point of water. What happens when I add a solute to water? Well, we know that the boiling point will be raised, right? So at 1 atmosphere, it's going to boil at this higher temperature. So it looks like my liquid phase, or my substance stays in a liquid at a higher temperature, and my substance stays as a liquid also at a lower temperature. So the liquid phase becomes bigger in my phase diagram. It occupies more area when I add a solute to my pure substance. And that's true for all solvents, not just water. Okay, well, let's try a few problems. Well, before we try a few problems, let's talk about a couple of practical applications. If you live in Utah, where we live here, you notice that there are trucks that not only plow the roads, but they also spread salt on our roads. And you might ask yourself, well, why do we spread salt on icy roads? Well, because when we spread salt on icy roads, it lowers the freezing point. So, of course, water normally freezes at 0 degrees Celsius, doesn't it? So let's say it's negative 3 degrees Celsius outside. So if it's outside, it's negative 3 degrees Celsius. My water would be frozen, and it's difficult to drive on icy roads. However, what if I add salt to the surface of that water? Won't that lower the freezing point? Yeah, it might lower the freezing point to negative 5 degrees Celsius. So now, if it's negative 3 outside, won't my water now still be in the liquid phase? Because it won't freeze now until negative 5. And it's easier to drive on wet roads than it is on icy roads. So that's one practical application. We also spray de-icing agents on airplane wings. And of course, that prevents water from freezing and jamming up the mechanisms, which can help the plane gain altitude or lose altitude if it's trying to land. And so we don't want those mechanisms frozen, so we'll add a de-icing agent to lower the freezing point. Another practical application that you might be familiar with is making homemade ice cream. Now, you'll notice that there's ice around this container. So there's a container here where there's cream and sugar and all sorts of good stuff. But outside that container, there's ice. Now, it turns out that milk freezes, or cream, freezes at temperatures lower than 0 degrees Celsius. So if I were to just put that cream and surround it by ice, which would melt at 0 degrees Celsius, it would just make my cream really, really cold and it wouldn't freeze it. However, if I add salt to this ice, once again, I'm going to lower the freezing point. And so, of course, water normally freezes at 0 degrees Celsius. If I can get it to freeze at negative 5 or negative 6 or negative 7 or even lower degrees Celsius, I can freeze that cream. I'm not sure what the freezing point of cream is, but let's say the freezing point of cream is negative 4 degrees Celsius. If I add rock salt or salt to my ice, I can lower the freezing point to -5, 6, or 7, or maybe even lower, and so I can get it below the normal freezing point of cream, which will allow the cream to freeze, and you would have iced cream. Okay? All right, let's try a couple problems. Let's calculate the boiling point and freezing point if I take 300 grams of C2H6O2 and I dissolve it in 800 grams of water. Now the first thing we need to do is calculate the molality of the solution. Remember, let's go back to the previous page. In order to find the boiling point change and the freezing point change, we need to know the molality of the solution. So let's do that quickly. We have 300.0 grams of C2H6O2. To find the molality, we need to go from grams of C2H6O2 into moles of C2H6O2. So let's see what 1 mole of that weighs. We have 2 carbons, and each carbon, as you recall, weighs 12.01. And we're going to add to that the weight of 6 hydrogens, and each hydrogen weighs 1.01. And we're going to add to that the weight of 2 oxygens, and each oxygen weighs 16.00. So I get 62.08 grams per mole. So now I have moles of solute, and molality is moles per kilograms of solvent, which in this case is my water. So 800.0 grams is 0.8000 kilograms. So 0.8000 kilograms. So let's see what our molality is. 300.0 divided by 62.08 divided by 0.8000 gives me a molality of 6.04 molal. Now I'm not finished with the problem. I simply know my molality. So my boiling point change will be my boiling point constant, K sub B, times the molality. So what was the boiling point constant for water? So let's go back and look that up. Boiling point constant for water, boiling point elevation, looks like it was 0.512 degrees Celsius per molal. So we have 0.512 degrees Celsius per molal solution, and we'll multiply it by the molality 6.04. So we'll end up with the boiling point elevation. So 0.512 times 6.04 gives me a boiling point elevation of 3.09 degrees Celsius. Okay, now my normal boiling point of water is 100. I'm going to add to that the boiling point elevation, so the boiling point of my solution will be 103.09 degrees Celsius. Okay, now let's do the same thing for freezing point. So that would be Kf times the molality. So let's look up the freezing point constant for water from the previous page. The freezing point constant for water is 1.86 degrees per molal solution. So 1.86 degrees Celsius per molal solution times the molality, 6.04 molal. Let's see what that gives us. Gives us a freezing point depression of 11.2 degrees Celsius. So normally water freezes at 0 degrees Celsius. We're going to subtract the freezing point change, 11.2, so my freezing point will be negative 11.2 degrees Celsius. When I add 300 grams of this non-ionic solute to water. So it boils at a higher temperature and freezes at a lower temperature. That means that liquid phase area of my phase diagram has expanded. Okay, now the practical use of this for lowering the freezing point and raising the boiling point is when we use our automobiles. They require an engine to have a liquid circulating around it to keep it from overheating. So we add something called antifreeze. Now, of course, antifreeze, as you know, lowers the freezing point, right? So it prevents water from freezing in your car's engine. Remember, when water freezes, it expands, and that can actually cause some serious damage to your engine block. If it expands, it can crack it. So we don't want that to happen, but it also raises the boiling point. So we can keep the water in a liquid phase at a higher temperature so we can circulate it around the engine and continue to cool it off. So antifreeze actually does two things. Lowers the freezing point and it raises the boiling point. And that's why we add that to our car's water. We mix it with water to lower the freezing point and raise the boiling point. Okay? All right, that's good enough for now. We'll work on another problem on our next video, and then we'll move on to the last colligative property. All right, see you soon. Bye-bye.